All right, so this is the reflection. This is A prime. This is C prime. This is B prime. Wonderful. So, coordinate for A prime is 2, 8. Coordinate for C prime looks to be, if I did it correctly over here, 2, 4, 6, 5. And B prime looks to be 2, 2. What do you notice about these coordinates and their connections? They're numbers. What else, Zayden?
The y coordinates are going to be the same in the respect as the y-axis.
Gotcha. So our rule is this. If we start out x, y, after we reflect it, y stays the same, but what happens to x? Y stays the same, but what happens to x?
X turns from negative to non-negative.
Good. It changes the sign. In other words, if it was positive before, it's negative here, and vice versa, right? When we negate something, it means change the sign. Doesn't mean necessarily make it negative all the time, right? Because if that x was a negative, and then we negated it, what would it end up being? Positive, right? So this is the rule. So when you flip across the y-axis, this is what happens. Now, if we go down here, if we flip across the x-axis, this guy, here's A prime. I drew this very poorly this hour. Sorry, guys. Here's C prime. Here's B prime. C prime looks to be 5 to the right, and then down 3. B prime appears to be 3 to the right and down 7. A prime appears to be 3 to the left and down 3. What do you notice about those coordinates? What's the rule? Go ahead.
Me?
Yeah.
I was just going to say all the y's are negative.
So we started out here with some xy pair, and our y's became negative, otherwise known as they changed their signs, right? Did x change at all?
No.
Nope, so it stayed the same. So again, this is the rule for when we flip across the x-axis. Now, how teachers will typically do this is they'll say, look, you need to memorize this. When we flip across the y-axis, this is what happens. You change the x. And when you flip across the x-axis, this is what happens. You change the y. And then they move on with their lives and say, look, you guys know reflections now. I don't believe in that. I think it's garbage. I don't think it's actually learning. You memorize it, and then you'll forget it, and then you'll not remember how to do this, which is a waste of everybody's time, so why even do it, right? How we're going to do is we're actually going to think about what's going on. Because what I'm going to require you to do, unlike most teachers, instead of just flipping it across this or flipping across that, what if I wanted you to flip it across, I don't know, that? Right? So we're going to actually understand what's going on here. First off, instead of thinking, oh, when you have a y-axis flip, you change the x. Here's how I want you to think about it, right? When we flip across the y-axis, that's the up and down, right? Okay? Notice what's happening to these points. Which direction are they flipping? Which direction? Right. Otherwise known as what direction? The horizontal direction. So when we flip things horizontally, what's changing? The x or the y? When we change things horizontally, what changes, x or y? X, because x is the horizontal variable. Duh. Right? We're flipping it horizontally. Did we change anything about these vertically? Did these guys change vertically? No, they're still the same height from the axis, right? So nothing changes for the y, but something changes for the x. Right? We're changing them from left side to right side. Good. Good. That'll, yep.
What happened?
We're going to have a fire drill, but we're not going to do anything with it. So I'm just going to sit in here and just keep teaching.
So we're just going to have to let it rip our ears.
Yes.
Did you say naughty word?
Which naughty word? I can say them all.
All right. All right. So I don't know why that was funny, but it was. Well done, Xavier. All right. So these guys flip horizontally, so of course the x is going to change. Now what's happening here? What direction are these flipping? What direction do these flip? Vertically. So of course we're going to have a change in the y. The x is going to remain the same because they're still going to be the same distance left to right. This guy to this guy, they didn't change left to right. They only changed up and down. They changed up and down. They changed in the y direction. That makes sense. That's what's going on. Now we're going to talk about this more formally at a later date. We're not going to do that now. Just wanted to give you a little taste of it. What we are going to do is we're going to review our notes from yesterday because we didn't have an official lesson on it. Here they are. So put that away. Remember, parallel lines, the symbol for parallel are these symbols right here, and not parallel is a slash through it. Parallel lines go off at the same angle. Vectors are similar to lines in that they can go off at an angle. They're also similar to rays because they look a lot like rays. Although a ray goes on forever.
Hi, Ray.
Hi, Ray. Vectors do not. They actually stop. We have a terminal point, right? We go from A to A prime. We're traveling, right? There represents a distance. Vector components consist of a horizontal and vertical component, similar to how the Pythagorean theorem works, right? This vector down here, vector V, has a horizontal component of 3 to the right and 2 up for its vertical. So we write that as this. Horizontal component's this guy, vertical component's that guy. And then we know that the rule is that whatever your original coordinate was, you're going to add 3 to the x and 2 to the y. And that's what this vector does to things, right? So vectors are movement. We learned yesterday as well, really briefly, that vectors are parallel if they have the same ratio of their components. So here are the components for this guy, 3, 2, right? The 3 is the horizontal, the 2 is the vertical. The ratio of their components is 3 over 2. Or 2 over 3, whichever one you want, right?
Whatever you prefer.
This guy is 6, 4, meaning that it's 6 in the horizontal, 4 in the vertical. Here are the components. If you're going to put the 3 on top, better put the 6 on top. Horizontal's on top, right? Or if you want to do it like slope, always do the vertical on top. Up to you. Doesn't matter. As long as you're consistent. 3 over 2 is the same thing as 6 over 4, because when you reduce that, you get 3 over 2. Therefore, these are parallel, right? They're heading off at the same angle. It appears to be 30 degrees for this guy. And, of course, 30 degrees for that guy as well, because they are parallel. Are they the same vector? No. Vectors are two things, direction and magnitude. Magnitude is size, and size does matter, unfortunately, for you, Mr.
Yep.
Mao.
Yep.
So they're not the same, but they're pretty similar. Turn the page. Kind of like Alex and Danny. Both going in the same direction, just different size. All right. I didn't say that. I didn't think that you were Jacob. I thought that she was going to say, yeah, Alex does not stop talking about you at home. And I'm like, yeah, that doesn't surprise me. The kid can't shut up about me in class. All right, so especially his sidekick Daniel Mao. I feel like
Sidekicks, but we don't
I feel like Jenna should be jealous of me, right? Right? Vector magnitude. Magnitude is the size. Magnitude of vector is the distance from tip to tail. Tip to tail is what we're talking about. Tip to the tail. Magnitude is directionless. We can calculate it by using Pythag, right? 12 in this direction, 5 in that direction. How big is the vector? What's 12 squared plus 5 squared? Yeah.
169.
169! Nice. All right. So, and then we root that for Pythag to figure out how long this is. And it turns out it's 13. Right? Again, these are the symbols for magnitude. Kind of looks like absolute value, right? And there's a reason for that. We'll also see it like this. Vectors is translation. We use the vectors and apply them to the vertices. Why do we call them vertices? Because remember, angles have a vertex, right? It's the point where the two little rays connect. So we have triangle. How many angles in a triangle? 3, right? That's why they call it a triangle. So we have 3 angles, which means we have 3 vertices. These are the vertices, A, B, and C. If we apply the ray 6, 3 to A, B, and C, it's going to transfer over to A prime, B prime, and C prime. Our new triangle location, we're just sliding it over. That's the deal. 6 to the right, 3 up. Am I blowing anybody's mind?
Of course not.
Just a little bit.
Okay.
The same way, just in
All right, next one says, translate this triangle by 3, 1. Okay, so that's 3 to the right and 1 up. Here's the vector. If I imagine copying and pasting that vector to all the points on our original triangle, we call that the pre-image. Then I do that, I get my new points, my image. X prime, Y prime, and Z prime. And it's okay if those points overlap. What we didn't do yesterday was this. Applying the vector is easy. Finding the vector takes a little bit more doing, but not too hard.
That looks really hard.
I know, right?
Oh my god.
So what we just did is we said, hey, there's this.
Who is it?
Probably.
Dylan, check
Nico. Where? He just walked by.
Nicholas Allen.
One behind you.
Nick.
Yay.
Right there.
Yay.
Oh, no, Dylan, you sit down. Go ahead and get it.
I don't see a Chrome book.
Dylan,
Hey,
you
change
try.
the map. I'm sick and tired of winning everything. Disappointing. You should.
I'm gonna ask them.
Alright, next time I say we cross the walks.
All right, so before what we were doing is we're saying, hey, here's a pre-image. I want you to send that to the new image, and how are you going to do it? I'm going to give you the vector and tell you what to do, right? So if I told you that I wanted you to move this image by a vector 2, -1, what would that mean we'd do to this? If we move everything 2, -1 by the vector 2, -1, Danny?
Move everything down 1 and 2 left.
Yeah, so 2 to the right because it's 2, right? And then down 1 because it's -1 for the vector, right? And that's what would happen. What they're saying is, look, I'm giving you the pre-image and the image. I want you to figure out the vector, right? And the way we can do this, we can look at the coordinates. If you look at these coordinates over here, we've got 2, 6 going to 9, 3. So what happened to go from 2 to 9? What was the change from 2 to 9?
7.
We added 7, right? Now, if this is a translation, which it is, then that should be true for all the points. Does 6 to 13 change by 7? Does 6 to 13 change by 7? Yes, it does. So it looks like we have a +7 rule for our x, right? What about 6 to 3? What happened there? -3. 8 to 5. 5 to 2. -3. So that seems to be the consistent rule. Therefore, this is a translation, right? And our rule was add 7 to the x, subtract 3 from the y. That's the vector we were using, 7, -3. And you can see that by drawing in those vectors, we can do it geometrically, right? And I can look with Pythag and figure out that, look, from b to b prime, I went 7 to the right, and I went down 3. What I'm doing here, right?
C.
What's the magnitude of this vector? 7, -3. What would the magnitude be?
Magnitude of 7 -3. Magnitude. Is magnitude?
What would the magnitude be? Magnitude is the size. How would we measure that vector?
Oh, magnitude's the size? A squared. You find the area.
Yeah, Pythag, right? So here's the vector, right? So we have a component of 7, a component of 3. What's 3 squared?
Supposed to do
9. What's 7 squared?
49.
What's 49 and 9?
58.
58. Root it.
Don't know.
Root 58. That's it. Root 58. Sounds like a fun place to drive. That would be the magnitude. So that's it on vectors of translation. Here's the deal. Sophomores, you're gone tomorrow, right?
Oh, dude.
The entire day.
Are we gonna party
Are you a
tomorrow?
sophomore, Danny, or a freshman? Yikes.
What do you think? Yeah, you think it's
There's still hope.
I'm a
All right.
senior.
All right. So because there's 7 of you gone tomorrow, which is not a very big number, I have another class that has literally 3 kids showing up tomorrow. We are going to press on. Okay. But that class is going to be behind, so I don't want to press on too much today. Okay. So what we're going to do is we're going to get the homework out right now. That's right.
Sign that back. Stop complaining. Sign that back.
That's right. Stop complaining, you whiners.
We were homework for now. Hey, we should all protest by lighting the classroom on fire.
Sounds like my grandma's house. My grandma, she rides a motorcycle on a scooter.
In a stable line.
If more of you were going to be gone, we were going to have like a picnic on a retreat. Sorry.
Hey, why can't you be a sophomore already? What is supposed to be one?
This is my fault.
Sorry, guys.
I know.
Mr. Mack,
Shoot your shot.
should probably complain about not getting it. There's a high chance I wouldn't do it.
It doesn't even look that bad like that.
Xavier, you protest.
Can I just do it now?
I mean, that's what we're doing.
Go to the
We're doing
bathroom.
right now, so yeah.
Everybody take a bathroom break.
No, we're not doing
I
that.
have to go to the bathroom.
No.
I legit do.
Okay, go. Just don't go in here.
Hey, no one's allowed to go to the bathroom until I go to the bathroom.
I'm going to the bathroom.
Xavier, you have lost your bathroom privileges.
I will stab you, Zach.
Do it. Let's see it.
I want to see that.
We're going.
Where are we going?
You told me to, Mr. Mack.
No.
Oh. I am sitting
Get out of
there.
my chair.
I'm sorry. I was put here.
Throw bricks at people.
Most people don't want to go. It seems no one goes on Tuesdays anymore and just goes on Fridays, which is great for my social life.
I think there were more people last Tuesday than Friday.
No. Friday was insane. You weren't here, were you? No, you were here.
Yeah, there were 6 of us here on Friday, and then there was 8 of us here.
There was more than 6 on Friday, wasn't there?
No.
I thought we had. Oh, okay.
Then Griffin, Gabe, and
Got it.
some other 3 people.
Yeah, I can make this in the chat.
Read your email.
Email?
Wow.
Whose email? My email?
Where's Headfit?
Is this due next Friday?
No. Dude, this Friday.
Yeah. I know. Yes! Erica, I'm so glad I can make you happy. All right, so. First bit, tell which lines are parallel using the symbol for parallel. This is so freaking easy. All right, so which 2 lines are parallel?
The ones next to each other.
Okay. Anyone else? A and B. A is parallel to B. Use that symbol, or you can write it like this. I don't care.
The ones
Mac, I still don't have a paper.
Okay.
He's sick and tired of you.
Your oily forehead keeps leaving like.
Oh my god. That wasn't even my forehead. My forehead can't get that oily. It's
I'm your favorite student.
3 hours
Shut up.
to the shower.
All right, 2 and 6. What do we know about 2 and 6, given that the lines are
Far
parallel?
apart.
Very good. Cap. So they're congruent. 8 and 4 are congruent as well by vertical angles. 1 and 3 are congruent. 5 and 7 are congruent by cap and vertical angles. What are connections? Other connections can you spot? Who cares? Moving on. All right. When we draw vectors, it is assumed, and you know what assuming does to us, right?
Sounds
Right? It is assumed they are coming from the origin. Okay? So, when we graph the vector 3, 2, we are starting from the origin, and we are going out to 3, 2. So here's 3 to the right and 2 up. That's where we're traveling to.
Alright, don't make it a big deal. It's just a word.
So it's not a coordinate. It is a vector. You need to draw it in. Okay? We assume it starts from the origin. Could we start it from anywhere else? Sure. Why not? But we're going to start them all from the origin for this. Okay? The next one is -1, -2. Has a horizontal component of -1. So that's 1 to the left. And 2 down for its vertical component. So there's its vector. Let's use Garin for 6, 4. 6, 4 is 6 to the right and 4 up. And what do you notice about this vector?
That it is not a straight line.
Overlaps with the blue, doesn't it?
Done
So what are we going to do?
Nothing and just like.
Yep, that's it. Don't freak out. It's fine.
it.
4, 8. 4 to the right, 8 up.
ASS. Ass you. Ass to me.
So there they are. Which ones are parallel?
Chase the money, chase the money.
Which ones are parallel?
It'd be 6 and 4, 3, 2, and
6, 4, and 3, 2. The green and the blue are actually parallel. They're going off in the same direction. And the reason for this is because you can take their parts and put them in ratio. What's 3 over 2 and 6 over 4? Are they the same? Oh, yeah, they are, right? So their components have the same ratio, which means by definition they are parallel. So we know that the blue vector, this one, 3, 2,
chase the money.
is parallel to 6, 4.
Depression.
And here's our parallel symbol.
Cool.
How do we know that? Because 3 over 2 equals 6 over 4.
What are like drawing parentheses?
Those are vector brackets.
Oh.
So you know you're talking about a vector and not a coordinate when you have pointy. So those are parallel. The rest of them are not, and you can prove that by comparing their components, right? 4 over 8 is not the same thing as anything else on here. Now we're going to find the magnitude. You need to do this for all of them. I'm just going to do it for one of them. Let's find the magnitude of 3, 2. Now remember, magnitude, the symbol for that is this. It's like absolute value. I'm going to do with the double version. The magnitude of 3, 2 is going to be whatever the Pythagorean theorem is, right? For those two components. That's going to find us the length of the vector, otherwise known as the magnitude. Right? Just like distance formula. What is 3 squared and 2 squared added together? 13. So root 13 is how long the blue vector is. That's its magnitude. It's how far it's pushing stuff. What direction is it pushing? Well, that's its components, 3, 2. Do that for all of them. Turn the page. It says translate the given triangle by vector 5, 9.
5, 9?
Yeah.
5, 9.
So we're going to apply vector 5, 9 to all these points. I'll do the first one for you. Let's do A and translate it by vector 5, 9. So here's our vector 5, 9. 5, 9 means 5 to the right. 1, 2, 3, 4, 5, and 9 up. It's good advice. You guys have been like doing that the entire time. Ladies in the back, you've been doing it the entire time with this like low mumble, which is like fine, it's cool, and like you do what you want. I know, but it's like getting annoying. So just make it a little less of a mumble. You can keep talking, just make it a little less. All right, up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So A to A prime is this. How did we get there? Well, we used this vector to get there. The vector is 5, 9. So we took A and translated it that direction. Now, to translate the whole image, we need to translate all of the vertices, right? So you need to do that for B and C, and then draw your triangle. Now, this is not the line for the triangle, okay? That's the vector. That's the vector. We're going to take that same vector and apply it over here, and it's going to show you where C prime goes. Now, we're not rotating or flipping or doing anything to this image. So if A and C are horizontally apart, like they are originally, they better still be horizontally apart when you move them, right? We're sliding the image. We're not rotating. So slide that image. The last one on here, we got one more page. Show me the vectors too. This one says, find the vector that represents the given translation. So they gave you an image that's been translated. Now, which one's the image in the which one's the pre-image? Pre-image means the original. Which one's the OG? Which triangle? How do we know?
Probably the one that's bolder.
No, the one
Good guess. Catherine.
The one that's lower.
Why?
Because it doesn't have the prime.
Exactly. Prime means new. Think transformations, Optimus Prime, right? We have A, B, C. A travels to A prime, B travels to B prime. So that's the direction we're going in. If you goof that, your vector would be going the other direction. It'd still have the same magnitude, but again, the direction would be different, right? So find the vector that takes us from A to A prime. Well, that's not hard to do.
-5, 3.
There it is. Find its components, right? Now, because this is a translation, every one of these vectors is going to be the same vector, just starting from a different location.
-5, 3.
Ah, triangular prism. Yum.
Beautiful.
Wow, that's hot.
Now, tell me what those vectors components are, and then call it a day. The last one, it says, define the following terms: vector, parallel lines, and vector magnitude. Draw a vector, label it, find the magnitude, and label the horizontal and vertical components.
Ew.
So, you got definitions for me? And you've got to make your own vector down here. Find the magnitude, find the two components, right? What is it? The two little brackets. Let's define a vector. Victor?
Victor,
What is a vector?
you spin your name.
Ah, wonderful. It's in your notes. Great. We'll skip it. What about parallel lines? How would we define those?
Oh gosh.
How would you define parallel lines? Good. It's in your notes. We'll move on. Magnitude. Good. It's in your notes. We'll move on. Rest is yours.
Here's where I drop
What's up?
Not much. Rest of the class time is yours. If you need help, you may ask for help. If you are struggling, I would encourage you to ask the person next to you first, because life's not about what you do, it's about